initialized data segment, and heap as well as stack. Now this heap at starting, this heap grows upwards. That means at starting this heap will have an address of an after any uninitialized data segment here exactly. There it will start. So this at starting, that means we can say that at starting program break is equal, program break is, where is program break then? Program break is at end of BSS, right?
No.
Where the program, where the BSS is ending, there heap is starting. So it is nothing but start of heap. Okay, so at starting initially program break is there. Once you start allocating it, then it will increase upwards. Okay, now here what happens now is when we increase the program break, then your program will be able to access any amount of here. Now this is the section we have for heap. Okay, now suppose we have allocated some amount of memory in this, but what happens is it will allocate, but it will have no physical memory yet. When we say that, when it will have physical memory is when we attempt to access that.
No.
Okay. Once we write a program that allocates some amount of memory, we will have some address to be accessed, but it will not have a physical location. But once we access that particular location, that particular location, automatically it will allocate physical memory. Okay. Now here when we want to change this program break, and when we do that, program break changes, then program break will have next address, which is not start of heap. Okay, now how to manipulate this program break, how to change this program break? We have two ways of doing it. So the first one is here using a function called BRK, and second one is using a function called SBRK. By using these two functions, we can alter the program break. Okay, and both are in library unistd.h. Okay, and the syntax for this will be okay. Now this is the syntax for your break. What does it return? So basically what we are using BRK function for, so we are using BRK system call to set the program break.
Okay.
Okay, so here if at all if it is executing properly, it will return as 0, or else if on success it will return 0, and if you have error it will return -1.
Okay.
Okay, now okay, once I'll say you the syntax for SBRK, and then we will continue further. So here now I'll just explain this also. So here also what it will return is, it will return the previous program break. On success and -1 on error. We will just see this, and this particular int ptr_t is an integer data type. Okay, now first coming to your brk system call. Now where it is setting to, brk system call sets the program break to the location specified by the end data segment. That means if we are saying that we will have a 10 locations in our heap, we are allocating some 10 units of memory. So this will point to the last memory location, 10th memory location, because it's growing upwards, right? So it will just point to the end data set, which is pointed, 10th is pointed by this end data segment pointer. Okay, now here we have one more thing, that actually we have discussed something about virtual memory, right? And virtual memory is allocated in units of pages. We have some pages in virtual memory, right? It has some particular KB of memory, that each page is of particular size. Okay. So if we are allocating some memory, so this end data segment will be rounded to the next page boundary. That means even if we have allocated some less memory, it will be bounded to the it will be rounded up to the next page boundary.
Okay.
Okay. So it will not have, basically it will not be pointing to the middle of the page or something. Once you allocate that page, you will be pointed to the boundary. Okay. Now suppose if you have something, okay, now what happens? Now program break current, what we said is start of heap is nothing but program break. Suppose initial value we are giving something which is less than that. Program break is there, right? Program break initial value is nothing but initial program break is nothing but end of BSS or start of heap, we can say, right? Suppose we just assign it a value which is below its initial value. Okay. Below its initial value, in the sense we have assigned memory in something like BSS or outside this heap section. At that time we get an error called segmentation fault, because we are trying to access a memory which is restricted or not allowed, which is outside its boundary. Okay. Now, but then this is fine. This is the initial program break. This is for below its initial value, we get this. Below initial value, we get this error. Then what is the limit of it? Upper limit. We know the starting, but what is the upper limit of your program break, where we can set it? Like I have upper break at 100, 200, 300. How much is my upper limit of my program break, where I can set it? Upper limit of program break. Now that depends on various factors. Okay, so like here we have each process will have some resource limit, right? How much resource a process can use will already be defined. Okay, so here that depends on the process resource limit. Limit per the size of how much size it's allocating for the size of your, we can say, segment, size of your heap data segment. Okay, next what we have is, second point will be something like you will have something called, now I have three things which we have not discussed yet. We will discuss in future, but process resource already we have seen this, so that's why I have said you. But this I'll just say you, location of memory mappings. We will discuss this later. And the third will be something like shared memory segments. The shared memory segments also we have not seen. This segment again comes in between stack as well as heap. Okay, if you can see this pic, here you can see this line, right?
Yes.
In between stack and heap we have some line, right? So there you will have something like, in between stack and heap we will have something called shared memory segment. And the fourth one will be shared libraries. So your upper limit of your program break depends on all these factors. So we can't say that you will have this much amount of this is the upper limit of break to assign the memory or not. It depends on various factors.
Okay.
Coming to your SBRK. Now, how this is used? When we call SBRK, what it does is, it will increment your program break. It will increment program break. Okay, so whenever we call SBRK, it increments program break. So internally, it is implemented on top of BRK. Okay, so basically you are using break to allocate some amount of memory, and after that SBRK just increments by adding program break. Okay, it just increments the program break. We can use it directly also, but it will be incremented by particular number. That's it. So basically, SBRK, here BRK gives us the location. We are giving the location to BRK, that we want specified, we will be giving some location that we need this much. So here SBRK adjusts this program break by adding increments to it. It will increment like +1, +2, +3. Okay, so basically SBRK is generally implemented on top of BRK in Linux. Now what happens when we give something like SBRK? So here if you see the syntax for it, the syntax for this is something like increment, and this intptr_t is an integer data type. This variable is increment, and we will be pointing to that next incremented address. Okay. Now if we write SBRK 0, what happens? Increment without incrementing, just if we write SBRK 0, that means program break. I am just writing PB for program break. Program break is it will return the current settings of program break. It will return current settings of program break when we write sbrk 0. Okay, and it will not change it. Why? Because 0 doesn't increment anything, right? So it will simply give us the current setting.
No.
We have seen this sbrk and brk for now, but generally what C programs use or programmers use is to allocate and deallocate the amount of memory on heap is whatever functions we know in general in C is nothing but malloc.
No.
Right. Generally we use malloc to allocate and deallocate the memory on the heap. Right. But what is the advantage of using this sbrk or brk over this malloc? Advantage of malloc on over this brk or sbrk, because sbrk or brk we are not seeing general.
No.
So what are the advantages of using malloc or the malloc, cloc or gloc? What are the advantages of using these? So one is something like they are standardized in C. Right. Generally when we use C, it is a standardized part of C. Right.
Yes.
So we just consider it as a part of C language. That yes, as malloc, cloc, all these are part of C language. So it's just standardized there. Right. Now, when we are writing thread programs, I think we have not executed thread programs, right? I forgot completely. Otherwise, I would have started with that. We have seen some thread things, right? We have threads, but we have not executed programs. So when we are writing threads program, it is easier to use this malloc in thread programs. Over brk or sbrk. And here what we discussed is when we are using this virtual memory, it is using in units of pages and it will round up to the next page boundary. But when we are using malloc, so what happens? It allows whatever amount of small memory we want to allocate. Okay, it allows how much memory we want in small units. In there, it was doing it in units of pages when we are using brk or sbrk. Okay, and one more is it allows us to deallocate or free the memory. Okay, it allows us to deallocate memory. So once our work is done, we are just deallocating it using a function called free when we are using malloc.
No.
Okay, and then what happens? Once we free that, it will be maintained on free list and it is recycled for the use of further calls when we allocate some amount of memory again. So the memory which is on the free list, it will be allocated again.
No.
So malloc gives us that advantage. That's why generally we go for malloc rather than this brk and sbrk.
Right.
Okay. And if we remember this malloc, it is also there in it is there in std_lib.h. If we see the syntax for this, This is there in standard library. So it gives us address of the allocated memory.
No.
So this we have used a lot of times in when we are writing program for this linked list and all. Okay, so when what it returns is allocated memory address if it is a success, and it will return null on error. Okay, but one thing we have in malloc is the allocated memory will not be initialized. Okay, it's not initialized. That means what? It may have garbage values. It's not an initialized memory, something like 0 or anything. It is uninitialized memory, so it may have garbage values. Next, we are using some function called free to deallocate this amount of memory. So what free is used to deallocate the block of memory which we have allocated using malloc. Right? So we can use free only when we use malloc or cloc or realloc. Not realloc, but either malloc or cloc. We can use it when we are using memory allocated using malloc or cloc. Okay, and this is also there in standard library, and the syntax for this will be void free whatever address we want to pass to deallocate that memory. Okay. So here if whatever address is returned, that address we can pass to this free to deallocate the memory allocated by using this malloc function. Using this free function. Now the question is, that means what? Once we are using malloc, the program break will increase in size.
Yes.
Because even malloc will also increase the size of your program break. Because we are allocating memory in heap. So whatever we use to allocate memory in heap section will increase the program break. That means if we are using malloc, then program break will shift. But does it lower its program break when we are using free? Free is nothing but deallocating whatever memory we have allocated. So now we have to deallocate that memory. So if I have reserved some 5 bytes or 5 units of memory, at that time free will just release this 5 units of memory. Okay, so will this decrease the size of your program break? That means program break is suppose set to 5 units of memory. So once we use this free, then program break will be is equal to again this what starting of heap or ending of BSS. You understood my point?
Can you tell it again?
Okay. Once we say we allocate memory, right?
Okay.
Once we allocate memory, program break will increase. Program break will increase to now if I have size of 5 units of memory, then program break will change to 5 units, 5 uses.
Yeah.
Okay, but when we free that memory, at that time, will the program break change to 0 again? Now suppose what I'm saying is, initially when program break is equal to end of your data in uninitialized data segment or start of heap, I call it as 0. I am calling it as 0. It's not 0. Okay. Just for explanation, I am saying it might be 0. So program break at starting is equal to 0. Okay. So once you allocate memory using malloc, so you are allocating some 5 units of memory. Okay, 5 units of memory I have allocated. That means what? Then my program break will be 5.
Yes.
Okay. Right. Now, when I am deallocating that 5 units of memory, if I am deallocating that 5 units of memory, then will program break becomes 0. Understood my point?
Yeah. Yes, yes.
Right. But it doesn't do that. Program break will not become 0.
Okay.
Okay. It will not become 0. Not be 0 again. But what it does is, it will add to the list of free list. It will add it to the free, what you can say, free block. So it will add it to the list of free blocks available. That means what? This 5 units of memory will be added for free blocks. So when again in our functions we call this out that we need some amount of memory, this free blocks will be allocated there.
No.
Okay. That means in future we are using it. I have freed it, but again in my program, again I am allocating some amount of memory. So this program break will not become 0, but instead whatever amount of memory is again required to be allocated, it will say that this is, we will have some free list, that these are the blocks available, free blocks available. So rather than allocating new memory, it will just allocate this free blocks of memory.
No.
Okay. But why do that? Why do it do that? Now, suppose we have used malloc 3 times. Okay. I'm just giving an example. So I'm just writing malloc 1. My first memory allocated it using malloc 1. Actually, I'm using malloc 1, but here this is my pointer, which is pointing to the point memory allocated by malloc.
No.
Okay. So this is malloc 1, this is malloc 2, and malloc 3. Now suppose I want to free some memory. But what I'm trying to explain is why your program break will not just free that memory and why it will keep it in free list. Okay. Why? Because now suppose I want to deallocate or free some amount of memory here. What happens if I just free malloc 2 before malloc 1 and malloc 3? That means this memory is allocated in between. First I called malloc 1. So it allocated some amount of memory. And then malloc 2. It allocated some amount of memory, and malloc 3 on top we have malloc 3.
No.
So basically we are trying to delete a memory which is in between.
No.
So as we are deleting a memory unit in between 1 and 3, your program break we will not be able to lower the program break.
Okay.
Okay. So malloc 1 at starting it had from 0 to 5 suppose. malloc 2 is from 6 to 10. and this is from 11 to 20. So here when we delete this 6 to 10, we can't just shift this malloc 3 to malloc 2. That means I can't shift these locations from 11 to 20 to 6 to 16. Okay. So program break will not be, we cannot alter the program break in this way. We can't lower the program break in this way.
Okay.
So that's why what it will do, rather than lowering the program break, it will just add the 6 to 10 in free blocks of memory. That these blocks of memory from 6 to 10 are free.
Okay.
And then again some malloc 4 tries to access that, it will just inform that this 6 to 10 is free. And you can allocate or recycle or use this memory.
Okay, yeah.
Okay. So, and one more reason for not lowering it is, whenever we are using free function, it will not release it completely. Okay. So basically we are going to leave that once we end our program. So it will allocate, release, reallocate. That's it. So it uses the cycle. Once you allocate the memory, release that memory or free that memory, and then again reallocate it. What we did here just now. So this is the reason program break will not be lowered or decreased. Okay, this is clear?
Yeah.
Right. Now the question is, then as it is not altering our program break, should we use free or not? We are allocating, releasing and reallocating. That means we are not completely releasing it using free. Free doesn't give us that complete access to release that particular memory. So should we use free or should we not use free? When our program frees completely, our program or it will release the memory completely only on process or program termination. Once we terminate our program, the memory will be released.
Okay.
Then why we have to use free? Right? You understood what I'm saying? We are using free function, right? But we are saying that by using free, we are not completely able to release that memory. We are just adding it into free list.
Okay.
Right. So should we use that or not? So two reasons are there. One reason of using free is it just makes your program readable. Readable, and for future modifications it's easy. Okay. So here it makes our program readable, like yes, we have allocated this amount of memory and we are releasing it. And again, if we want to just modify that, yes, we will have an idea that yes, already we are allocating and freeing this memory. That means we need not allocate new amount of memory or anything. Simply it makes your program readable. That's it. That yes, allocated and released. Okay. And next is something called memory leak. Now, what is this memory leak? Memory leak is, suppose what we said, it makes program readable, right? Now if I don't use free, at that time what happens? I'll complete again and again, I'll use this. There will be no free memory in my free memory list block. Free blocks. List of free blocks. Okay. So that means every time I write malloc function, we will create new block of memory.
Okay. Yeah.
Right. That means already we discussed that there is an upper limit for your program break. But if we don't free and reutilize that particular memory, it will breach at some point and your memory leak will occur.
Okay.
Because you don't have that much amount of memory to be utilized, but you are just going on allocating some amount of memory. Okay. So for that reason, it's better to use free function.
No.
Okay. And coming to again, other than this malloc also, when we use realloc for the same thing, sorry, not realloc, calloc. Calloc has one difference that rather than taking only one argument, it takes two arguments. So if you remember, we have something like enter calloc. It takes two arguments, which is size underscore t number comma size underscore t size. So here it gives us first what is the number of number of units of memory we want and what is the size of it. So if we say something like 100 integers, it's simply like 100 comma int. Generally we don't use int, we use structures only, but just for an explanation I'm saying. So pointer, it will allocate 100 units of integer memory. Okay, but one difference for this calloc and malloc is calloc is initialized to 0. So whatever 100 blocks of memory we have allocated, it will be all initialized to 0, which means it will not have any garbage values. Okay.
No.
And similarly, if we have realloc is used in combination with either malloc or calloc. Because realloc itself says that realloc is nothing but reallocating the already existing memory. So here it takes arguments like what is the previous pointer used. That means if we used something like here pointer equal to some variable name, pointer is equal to void of. So when you allocate this calloc, it will just return address of this 100 units of memory, initial address of this 100 units of memory. So that initial address we will be giving here, and then here next argument we will say is size. What is the new size of memory you want to allocate? So if we want something like new 100 units of memory, we can just say that. Okay.
Yes.
Now this was till now we have discussed only for allocating memory on heap. Okay, but
Yes.
we can allocate, generally what we allocate on stack, whatever functions or what variables, whatever we use in our functions will be allocated in stack memory, right?
Yes.
So once you call a function like int a, b, that a and b will be allocated in stack frame for that particular function.
No.
Okay, that doesn't use dynamic memory allocation. But we can even have dynamic memory allocation on stack. So allocating dynamic memory on stack is done by using a function called alloc. Alloc A. This is the function to allocate memory dynamically. Allocate dynamic memory on stack. Okay. Generally on stack we don't use dynamic memory allocation. Whatever dynamic memory allocation we use is for heap section only. But by using this particular function called alloc A, we can allocate dynamic memory on stack frame. Okay. Now, why we can use this? Okay, so generally what happens when you use functions, what happens? So here when you allocate some amount, generally what happens, once you call a function, it will allocate a stack frame, and once you return, that stack frame will be released, right?
Yes.
Generally what I'm saying about function is, so if you say I'm calling two function, that means function inside a function, one stack frame will be for function 1, and on top of it again one more for function 2. So till we come out of function 2, function 1 will not be released.
Yes.
Right. Function 1 will not be released. Once we return from function 1 to main, function 1 and function 2 will be released. Right. So that means what? Always this calling function is on top. Whatever memory we are allocating on stack is always on top. So if we call function 1 and then function 2 will be on top and function 1 will be below that.
No.
Right. So
Yeah.
when you do, as it is working in that way, there is space for expansion, because dynamic memory needs expansion. So as we can have space for expansion, as that will be the top function, that's why there will be space for expansion, and we will be able to use this alloc A function. Okay, and the syntax for this will be, this is there in library. The library for this is again different, which is alloc A dot h, and we have, it will return the address allocated. Okay, so if on success, it returns the pointer to the allocated memory, and -1 on error. Okay.
No.
Now here, as we are not using it on heap, or we are not using it along with your malloc or calloc, we will not be able to use free function as well as realloc function with this function. So we cannot use free function to deallocate this memory, and we can't use realloc function to resize this memory. Okay, we need not use free alloc. Why free function? Why? Because once you come out of that function, automatically stack memory of that particular function will be collapsed. Right. Once we come out of particular function, that stack frame for that function will be collapsed or deleted. So we need not worry about freeing that particular memory. Okay, so by using we cannot use this free function along with this alloc function. Okay, so there are some advantages of using this over other functions. So advantages are nothing but alloc A is faster. Alloc A is faster than malloc. Okay, and one more we have is we need not use free function. So without using free function, our stack frame will be removed. Why? Because once function is written, that particular stack frame for that function will be released, and that is the reason that makes an advantage for your alloc A function.
Oh.
Okay, but again we have some limitations also. Why? Because we will have some stack size frame. Again, the limit of this stack and all will be there, but generally we go for malloc or calloc only, but there are some stances where we need to use alloc A. We will see that. We will just write one example for this also, but not today. Shall I start next topic or shall we continue tomorrow? Up to you.
Yeah, we can.
We can continue. Fine. So this was some basics of your memory allocation, how the memory is allocated. Next topic we have is signal. Okay, so what is the signal? Signal, we have one of the main topics we have here is like process as well as thread. We have signals also. So I'll just give a brief explanation of this signal, but we will write programs tomorrow only.
Oh.
Okay, so what is signal actually? So here signal, we can say that it's just a notification to a program or process. Okay, that particular event has occurred.
Okay.
Okay, so it's basically just a notification we send or we get to a process, a notification to a process. I'm not saying program because program in execution is nothing but a process. So a running program, if it gets a notification that a particular event has occurred, that is nothing but signal.
Okay.
And sometimes we even call it as software interrupt. Okay, and sometimes we call it as software interrupt because of some software things also we may get an event triggered and a notification will be processed. Even we can say that they are similar to hardware interrupts.
Yeah.
Okay, why we are saying it is similar to hardware interrupt is because, see, we know how interrupts work, right? Interrupt is also nothing but a notification that particular event has occurred. Now when you get a call on your phone, and if you are doing some work, you will get a notification indicating your current task, because call is a high priority feature. Your YouTube, if you are watching something on YouTube or some video you are watching, that video will be paused and you will get a notification of call. Why you will get that is because video is low priority task and your call feature is high priority task, right? So for some time the video will be paused until you just release that that I don't want. At least you will have to swipe or use some option to not necessarily you need to answer it or click on it or wait till that call notification goes off, because nowadays even we have that feature that if we are watching videos we can just swipe it and yes, background the call will be there and we will be able to use the video without answering or without reacting to that particular call. Okay, but even though that it is an interrupt or notification saying that yes, you are getting an call. Okay, and it interrupts the flow of execution of your program.
Okay.
Right, and moreover we cannot say that when we will get that interrupt. I don't know when I'll get a call.
Yeah.
So that's not predictable. So that's why this is how hardware interrupt works. Similarly, the signals will also work like this. They may also disrupt the program flow of execution, as well as we cannot say when a signal will arrive. Okay, so they are almost similar to software as well as hardware interrupt. Now, you have something like a signal can send a signal, one process can send a signal to another process. That means one process can send a notification to another process also. Okay, so when we do that, we can say that we are using something like synchronization technique, or we can say we are doing inter-process communication, that we will see later. But basically a process can send a signal to another process also, and a process can send signal to itself also.
Oh.
That means a notification can send to itself. Now, what are the events? What we said, a notification to a process, that event has occurred. Now, what type of event it can be? What type of event can occur? What type of event can generate an signal? So, it can be something like hardware exception. Okay, now what it can be? Some fault has been detected. Okay, and that will be notified to your kernel that a fault has been occurred on some particular hardware device. Okay, and then what happens is that kernel will send the corresponding signal to the process concerned. Now, if we say if we have some hardware device, you can say a process is nothing but a device driver for your keyboard. So if at all, if a hardware fault is detected on your keyboard, then that kernel will send that particular notification to your device driver of related to keyboard. It's just an example. Okay. So there can be hardware exception where a signal can be sent to a particular process. Or the practical example is referencing to inaccessible memory. When you try to access a memory which is restricted, at that time a hardware exception occurs, and that will that will be sent to, that notification will be sent to kernel, and kernel will inform to that particular process that you are trying to access a memory which is not, or which is restricted. In this case, or in this event, signal has to be generated. Okay, and the other one is user generated, user typed. User generated, how we are generating signals. If you have observed, sometimes we are running a program in while loop. Suppose we are running a program in while loop and we are not exiting that loop, we are running. So at that time what happens, either we are using Control C or Control Z for that, to break the program execution. Okay, so at that time when you click on this Control C or Control Z, it is nothing but C is your interrupt character and Z is your suspend character. So when we use that, the program will be terminated. At that time we are generating a signal using this Control C or Control C or Control Z. Okay, this is user generated signals. Okay, one more way of generating your software event is, one more is your software. Okay, so one more is your software event, and that will occur like if some software event occurred. So what the software event occurred is like child process terminated. So when child process is terminated, that has to be notified to your parent process. So parent process will get a signal from your kernel that child process terminated. So in this case also, software event has to send a signal. So either we will get signals from hardware exception, from user generated, or from software event. In any way we will be using signals, or simply saying we will be sending some notifications saying this. Okay, and we have signals defined as integers. Okay, signals are defined as unique integers. That means what? In signals will have numbers. Okay, and it will start from 1. Okay, each signal will be defined as a unique number, and the number will start from 1. And all these are defined in one header file called signal.h. Okay, along with name of the signal. Like example, interrupt signal is there, suppose. So it will be represented as sig int, or you can say anything sig. Okay, I'll say int, and the number of that interrupt is, or the number of that signal is 2. So it will be represented in this way. Okay. All the signals will have some name representation like this, sig and then whatever name we have for that particular signal. Here we have integer. We may have some other signals also. So that particular signal name will be written in place of this x. Okay, along with number. So each signal will be given a particular number. That number will range from 1 to 31. That means we have 31 signals. Notification. Now signals will be classified in two categories. Signals are classified into two categories. First one we call it as either traditional or standard signals. Which are used by kernel to notify the process that notify a process that event has occurred. And as we just now we discussed, they are from 1 to 31. The other one we have is real-time signal, which we will discuss later. Okay, so these are real-time signals that we will have to write it. Oh, 3 I have the second one. So your signals are of two categories, traditional and real time. Now, how the signals are working. So basically some event occurred. A signal is generated or a notification is generated. Then what happens? Next, after this signal is generated, next thing is it is delivered to a process. Okay. Once signal is generated, it will be delivered to particular process. Okay. Who is going to deliver it? Obviously kernel will do that. Okay. Once generated, so that particular process will have to be delivered that this signal has been occurred. Okay. In between. And what after delivering? That means after a process gets notification that a signal has occurred, then that process what it will do, it will take some action in response to your signal. Okay. Saying that okay, this occurred, then what to do next? So first a signal will be generated and then it will be delivered to process that signal has been occurred, and then the process will execute that. If at all if this signal or notification came, then what to do, that will be taken care by the process. Okay. Now there we have one more term here, we call it as pending signals. So what is this pending signal? Pending signal is the time between generated signal, time between the signal generated and delivered. We call it as pending signal. Okay. So what we have seen that whenever an event occurs, that event will be notified to kernel first, and then kernel will send a notification to process. Okay. So the time between a signal is generated and it is delivered to process, in between whatever the kernel is doing to send the signal from that signal to send it to the particular process, we call it as pending signal. Okay, and when this pending signal will be delivered? Okay, we can say that why we will get this pending signal, because so once generated and delivered, you will have some pending time between. So it may have two things. One, pending signal will be delivered as soon as you get it. If the process is running, because we have something called context switching also, right? So different programs will be running. So my program or my process may not, if at all, if it is running currently, at that time it will be delivered immediately. Okay, if process is running, it will be delivered immediately. And if our program is in waiting state because of context switching, so at that time, whenever our process is scheduled, at that time that signal will be delivered. Okay, that's why we get pending signal. Why? Because our process may not be running currently. So when our process is not running currently, it will have to wait. Our kernel have to wait for our process to run. So once our again our process is scheduled to run, at that time our signal will be delivered to our process. So that is your pending signal. Okay. Now, sometimes it happens that even though if I get a notification, I should not be interrupted by that particular notification. Okay, I am getting a notification, but whatever work I am doing, so that work is more important, and that notification should not disturb my current flow of action. So at that time, what we can do is we can add our signals to, we can add that particular signals to process signal mask. Okay, so what is this process signal mask is? It is a set of signals whose delivery, that means even though we deliver, even though kernel delivers this, the delivery of this signal is currently blocked. That means even when we receive that signal, that will not interrupt the flow of our program. Okay, when we add that particular signal to process signal mask. Okay, and one more thing here will be then, and if a signal is generated when it is blocked, okay, when signal is generated while we have added it in process signal mask, which means we have just blocked it. So while it is blocked, then that signal remains in pending state until we unblock it. Okay, because why? Because even though that delivery of that signal has been done, but we have not taken any action in response to that signal. So that's why this signal is in pending state only. Okay, next you have it now. Okay, so we are doing this by masking. Now, how we can add or remove this from your signal mask? So we have various system calls to allow a process to add or remove signals from signal mask. Okay, we have various signal calls for that, system calls for that. Now, here after we, okay, so now coming again back to your action, taking action in response to, now we got a signal generated and that was delivered. After this delivery, what happens? So upon delivery, so here some action has to be taken on that particular signal. So that can be, what actions can be taken is depending on again signal. So that signal can be ignored. Okay. Signal can be ignored or signal is ignored, and this is done by kernel itself, and a process may not even know that this signal was generated. So either a signal is ignored, it cannot be, can be, signal is ignored. So why? Because here the kernel itself may ignore the signal and our process may never know it. That's why a signal is ignored. And the other one, if process is terminated, or we can say killed. Okay, so once we get a signal, either that signal is ignored or upon the delivery of that signal our process is terminated. Okay, so if it is terminated, then we call it as abnormal process termination. Upon receiving a signal, if process is terminated, we call it abnormal process termination. Okay, why? Because when normal process will be terminated when we call exit function, right? So when we call exit function, normal process will terminate. But if upon receiving the signal, if a process is terminated, we call it as abnormal process termination. And one more we will have is core dump file. Okay, these are the actions which can be taken on receiving a signal. Okay, core dump file. Now, this core dump file will be generated. And then process will be terminated. Now, what does this core dump file contain? It contains the copy of your virtual memory or the image of the virtual memory of that particular process. Okay, so this just contains one particular image of that virtual memory and it will terminate the process. So when you want to debug that why this process got terminated, you can check this core dump file to check out the or to debug it, that where the error was. Okay, and fourth one is upon receiving the signal, process is stopped. Stopped is nothing but suspended. Okay, it's suspended for some particular time, and a signal, we may get a signal even to resume the stopped process. So your signal will have these particular actions. Your signals can take these particular actions. Either a signal which is received is ignored, or the signal can terminate a process, or a signal can generate a core dump file and then terminate a process. Upon receiving the signal, a process can be stopped or suspended, and again upon receiving the signal, we can resume the previously stopped process. Okay. So these are some basic actions that can be taken by a signal. Now, these are the default actions. Okay, these are the default actions, but even we can change the action that has to occur when a signal is delivered. That we call it as disposition. Disposition of signal. Disposition of signal is program can change action. Change the action that occurs on deliver. That occurs when signal is delivered. Okay, so that's we call it, because these are the 5 default action which can be taken. But other than that, if we want to change the action that should occur when a particular signal is received, we call it as disposition of signal. Okay, now here this program can set the following dispositions. How these dispositions can be set? So first one is again same thing, default action. Default action is nothing but if we have done some dispositions, then again change back to, or you can say do Control Z, or you say undo operation can be done to get that default action. We have changed a disposition of a signal, and after changing this can be again turned back to your default action. So this can also be done by this disposition signal. And then second one is it can be ignored, and the third one is this we will have to discuss in detail, which is signal handlers. Signal handlers. Signal handlers are program, or you can say it is a function, not a program, but it is a function which we are writing, that we can write to do a particular task when this signal occurs. Okay, so as we are writing a function to do a particular action, we call it as disposition of signal. Okay, so we will be writing this signal handler functions tomorrow. Okay, because it will take so much time if we start the signal handlers. So we will do it tomorrow, and moreover we will have to discuss even by default whatever signals are available. That signals also we will have to discuss. That also I'll discuss it tomorrow. Time I'll say you either 8 or 9.
Yeah. So,
Okay.
Arun Sankumar, so if you can record the sessions when you are free,
Yeah. Okay.
so that's
So
also
will it
fine
be
for me.
okay for you?
Yeah,
Then that will be very much easy for me.
yeah, that's what. Any practical or anything we can have, or else of the theory classes. However, I have to revisit your recordings and once again I have to learn.
Yes, yes,
So
yes.
better you when you're free you can record it and it should be easy
Sure,
for you and me
definitely.
also.
That I can do it. That I'll
Okay.
do it. Okay. Thank you.
Yeah.
If you have any
Bye.
doubts in today's session.
No, as of now I don't have any doubts.
Oh, okay.